It turns out that the ground state energies of these self-consistent field approximation calculations are related to the ionization energies, or the energy of the positive ion, remove one electron, and the energy of the negative ion, where you add one electron. And so this tells us about ionization energies, and this tells us about electron affinities. So the epsilon sub k is the energy of the highest occupied orbital, and epsilon sub m is the self-consistent field orbital energy of the lowest unoccupied orbital. So if we take these self-consistent field calculations out to the first orbital that is not occupied, then we can obtain values for that energy of the lowest unoccupied orbital. And if we add that energy to the ground state energy, we will get the energy of the negative ion. So this is the amount of energy required or obtained when we add an electron to the atom. And that is exactly how we define the electron affinity. And if we remove the electron that is in the highest occupied orbital, so we subtract that energy from the ground state, that gives us the energy of the positive ion. So this epsilon sub k is exactly the ionization energy of the atoms. And so we can use these Hartree-Fock calculations to verify the periodic trends that we learned in general chemistry. So you may remember some rules from general chemistry for building up the electron configurations of the atoms. We've always said that you fill the 4s orbital before the 3d orbital, or the 5s before the 4d, etc. And we explained that by saying that the 4s orbital was lower in energy than the 3d orbital. But we can actually look at our Hartree-Fock calculations and see whether this is in fact true or not. And then we will be able to decide whether that was the right explanation. So you might also recall that if you're looking at fourth row elements and you're going to make an ion, we said that you remove the 4s electron before you remove any 3d electrons. And we had some hand-wavy explanation about why you should do that, and it wasn't very clear, but you just had to remember that you should remove the 4s electrons before the 3d if you're making positive ions from row 4 elements. So let's take a look at these two general chemistry rules in light of our Hartree-Fock calculations and see if we can figure out why these Aufbau, building up of the element rules, make sense. So I've shown here a graph that shows the difference between the orbital energy for the 4s and the 3d. And this is for the fourth row elements. So we can see that in fact that difference is always positive. So if we take 4s orbital energy minus the 3d orbital energy, it's greater than 0, which means that 4s is higher in energy than 3d for each one of these elements. And so that tells us that in fact this explanation of this rule is wrong. So it's not that 4s is lower in energy than 3d, but something else is going on here. So let's think about why this might be the case. So remember that if we sum up all the orbital energies, the total energy is the sum of the orbital energies minus that electron-electron repulsion. And so it turns out that obviously if we add in the higher 4s rather than the 3d, we're going to get a larger energy. And remember that it's the minimum energy that is closest to the true energy. So adding in 4s would make this total energy go up relative to the 3D. And so you would think we'd want to put the 3D in there. But if we look at the electron-electron repulsion term, remember that if we think about our radial probability for the different orbitals, that our 4s orbital has a electron probability of being in close to the nucleus. So it penetrates in towards the nucleus, whereas the 3D orbital does not have that penetration. So that means that these 4s electrons are going to be in closer to the core electrons more often, and are therefore going to have a higher repulsive potential with those core electrons than the 3D would. So if that electron-electron repulsion term for the configuration that ends in 4s is outweighs the higher orbital energies, then the 4s configuration is going to end up being the minimum energy. So it's this fact that the electron-electron repulsion, the self-consistent field, produces a lower repulsion when we minimize with the 4s configuration rather than the 3D configuration. So that's when we talked about penetration as being important to thinking about the actual electron configuration of the atoms. Remember that all these orbital energies are negative. And so if 4s is higher than 3d, it means that the absolute value of 4s is actually going to be less than the absolute value of 3d. So for example, let's say that 4s is at -2 Hartree and 3d is lower than that, so is at -3 Hartree. So if we take the absolute value, 2 is less than 3. That is, it takes less energy to remove the 4s electron because it's closer to 0 than it does the 3d electron. And so we will always get the correct ion configuration if we remove the electron that is easiest to remove, and that's the 4s electron.